Today, I'm actually gonna do this. So I want to basically, create a library that does automatic model distillation, right? So what this means is that, like, let's say you have a model with n parameters, let's say with p parameters, and l layers, and you want to create a new model such that p prime is less than p and L prime is less than L, where the loss between basically the model that uses P prime, basically P prime, L prime, and then like some data is like roughly equal uh, to the loss of P L data. Right, so this is sort of the problem that we're trying to solve. And in general, it falls within a trend of when you're trying to actually deploy a model to start doing a bunch of inferences on it. Like there's a couple optimizations that are, pretty popular, right? So basically for preparing a model for inference, often involves things like basically like model distillation, which is exactly what we're going to talk about, quantization, maybe some pruning, right? And then maybe there is like a fourth one that's like rounding up weight values. And what I mean by that is basically make matrix parameters powers of 8. This is, for example, like an NVIDIA GPU thing. So these are, for example, like eight, sorry, these are like four different things that you could do when you're preparing a model for inference. And at least like 2 and 3 have a good solution with TorchFX. All right, so this is TorchFX, and I'll be going over its basics in a second. Oh, sorry. Oh, okay, sorry. Like, I don't know if this was playing the whole time, so I'm just gonna start from scratch again. I apologize. Um, Here, let me set up chat in the background as well. I apologize, but this is gonna be like an interactive, like coding heavy stream. So if you've been looking forward to that, this will be the stream just for you. Okay. So, from the top. So, hi everyone. Today, what I want to be working on is a library for automatic model distillation. So the idea behind distillation is that, let's say you have a model with like P parameters and L layers. They want to create a new model that has fewer parameters or fewer layers, but where the loss on the data that you have is very similar, right? And so we're gonna talk about, well, one, how do these kinds of, like, how does distillation work? Like, sort of, what are the basics of it? And then how could we implement it in an automatic way? As in, like, let's say you already have some model, but now, you realize, like, well, it's a bit too slow, like the latency is high, or the throughput, so sorry, yeah, the latency high or the throughput is low. So traditionally, when you're trying to when you're trying to improve these performance numbers, there's a few things you could do. Like one is model distillation, like with things like Dilbert quantization, which is using lower precision numbers, pruning, which is just zeroing out some parts of the like of the tensors, and then a fourth one that's maybe like a bit weirder to think about, but like rounding up weight values. For example, like GPUs work over powers of 2 well, and like tensor cores work over powers of 8. So can we just sort of automatically take a computational graph and make sure that its values are powers of 2 or 8? So the reason I want to actually implement this, and even though doing it in an automatic way seems like kind of a hard task, I'm optimistic that this is solvable within the stream because of TorchFX. So quantization and pruning specifically have solutions in FX. And if you're curious about FX at a high level, it's a new library. It's beta, and again, this is not official opinion or anything. This is just like my personal opinion and why this library is interesting. But let's say you have for example this module, And then, like it has a bunch of parameters, and then it's just sort of the forward function is sort of a simple linear layer. And then you get a module and you trace it, and then you end up with this sort like with this sort of like lower level code. Hey Shreyansh, yeah, so it's too late in the night in India. Will this be posted to YouTube, and if so, by when? Yeah, so it should be on YouTube within like a day or two, so it'll be up very quickly. Yeah, I definitely appreciate the international time zone, which is why I do think YouTube has been a more popular place for people to view my videos, especially that I can't seem to commit to a regular schedule, not because I don't want to, but I mean, actually, no, because I don't want to. It's just, it's very hard to sort of, it feels too much like a job, I think, when I start doing that. So, yeah, regardless, I think back to FX. So we have a model, we're going to trace it, and then we basically get some traced code that we can work with, and then we can transform, right? So basically, yeah, let's go here, right? So FX lets you manipulate um, nn.modules as if it was data, right? So you can basically transform the graph and do stuff with it. So how do these transforms work? Well, you basically do this trace. You have a graph. You do some stuff with it, and then you return it, right? And so let me show you a quick example. So here, like, so for example, like they're printing it as a graph, but this is not the interesting part. Yeah, so for example, this one's interesting, right? So this is saying, okay, well, you go over the nodes of the graph, and if the node has a call, so if the node is calling a function, then you change additions to multiplication, right? So let's see. And so I think they had quantization maybe here somewhere. Interpreter pattern. Debugging generated code towards around the end. I had a notebook that I should have pulled out before the stream where I have a better example actually. Okay, so here, for example, like they want to no op in activation. So they're saying, okay, without activation, you have this module. And then with activation, this module. Okay, non-torch functions. Yeah, I think this doc needs to be a bit improved. It doesn't really express why this is such a cool library in my eyes. It's okay. So let's do this. So, before we talk about distillation or doing any kind of transformation, I thought maybe let's just do like a real. So I want to just pip install transformers. Right. So the dash Q is a new trick I learned. It just means quiet, so it doesn't print a bunch of stuff to my terminal. All right. So, and now what we're going to do is we're going to download a Hugging Face transformer, and we're going to see if we can trace it, right? So that's sort of like the basics. Hugging Face transformer. We say bird base uncased. I think they had a model hub somewhere. Where was it? Let's see. Hugging Face download bird example. Okay, yeah. So yeah, this is what I was looking for. So say we're looking for the bird uncased. Yeah, it looks exactly like this actually. So this is great. We're gonna do this. right? And so one thing I want to keep in mind is that like we do need to have an eye out for what we want the end level API to look like. But right now we're sort of building the individual pieces that we're gonna need, just as like a simple illustrative example, and then that'll help us like actually build a fully working. So it's like something that we can reproduce over any model, right? So right now, like what I want to show you is that let's say if you say print model, well, you can see a couple of stuff. Well, the first thing you can notice, for example, is that well, there's these embeddings. These token embeddings, type layer norms, there's like these layers, right? And then so there's this embedding part, and then there's an encoder. And this encoder seems to have, I would say, I think BERT is encoder only like 3, 4, 5 BERT layers, 6, wait, 4, 5, 6, 7, 8, 9. I forget how many layers, 10, 11. Sounds like, yeah. Okay, so we have an embedding. We have 11 layers, BERT layers, and in each of these BERT layers we have self-attention, which consists in a query key and value with dropout. So each of those things are um, basically like an operation. And then here we have the BERT self output. So so we have an output which has the number of features, number of in features, number of out features. We have layer norm. We have these epsilons, we have these dropouts. So, we can't just like look at all numbers here and just divide them by 2 like that. That probably wouldn't work. Um, and then okay, we have this head which has in features, out features, and then layer norm here. But the high level idea behind distillation will be it's 3 parts, right? So a prototype for effects based model distillation would basically accept an N model as an so basically let me just write up the API. So it's going to be basically something that says like uh, distill, and then this takes in like some sort of what's called a teacher model. So this is basically the base model that you're transforming. And then basically some scaling factor. So let's just say like a parameter scaling factor. So by how many parameters you want to reduce this, and then some sort of layer scaling factor. And then it's also going to need to take like some input data, and then it's going to also need to take in an optimizer, right? And then this would return a student model. Right? So this is sort of at a high level what I want the API to look like. And as an illustrative example, uh, we're gonna start with hugging face just because it's a model a lot of people care about. All right, so let's do this. So we have this model, right? And so now the first step that basically we're gonna need to do this. So let's elaborate on the steps that basically where the steps are. You download the Hugging Face model, trace the Hugging Face model, and get a symbolic graph. Navigate, basically copy the model, and then navigate the graph and change the right weights to divide them. 4, and basically 4, then do the run distillation using KL divergence. And I'll go over like how this works in a bit. But this is sort of like the high level idea behind how I'm thinking this could work. So let's just start with the symbolic tracing, right? Like, so we've downloaded the model, we've seen it, that's great. So let's just do the tracing. Get a symbolic graph, sorry. So here, so we have with torch fx, import symbolic trace. All right, and then we do this. And then we take in the model. Yeah, you cannot specify both input ideas and input embeddings at the same time. Okay, what is happening here? Oh, because it needs to be traced with an actual value. Right, so let's try this. So, oh, I see, because it does need to be traced, right? So I think let's try, um, I think this is going to do this. Cannot specify both input ideas. I'm not specifying either, though. So they're both not none input IDs and this. Can I get a breakpoint here? See what this looks like. Yeah, this feels like it does need a breakpoint. How do we solve this? Because here, for example, they're not really mentioning values at all. Um, symbolic tracer, it feeds fake values through the code. Okay. What is it giving it though? Is this potentially a bug? Um, so basically cannot specify both input embeds and input IDs at the same time. All right. So since this didn't work, what we can do is we can just pick a simpler model. So let's just do an example of a convolutional neural net PyTorch. Yeah, that's what I was thinking too. I was just thinking like, um, I guess, yeah, you're right. Like that's probably the simplest example, right? Let me just pull this out. Because I think like the CNN example is illustrative. Where was it? Yeah, something like this. All right, so let's say this is our model. Okay, so I forgot to import PyTorch. Import torch, and then torch.nn.module. Okay, great. So we're doing stuff. All right, so how do I... Okay, so now I want to symbolically trace this thing still. And I need to first create an instantiation of this model. So I can say CNN model equals net. Right, and then I can say here CNN model. So this should work. Sequential is not defined. Oh, I see, because it's, I think, torch.nn.sequential. Self.cnn layers. Nechui. There are two. Wait. Oh, yeah, I see it. Conf to D is not defined. For fuck's sake. What were the imports they used? Imports. Conf to D. Yeah, because is what I needed. Okay, I'll just get all of these for now. All right, great. So now if we say print symbolic traced, we can see our model, right? So here it shows, okay, well, we have the CNN layers, And then we have this batch norm, we have these conf2ds, we have these max pools. And then here you'll see the conf2d of size 4. Yeah, so I think actually maybe you're right, C. Garcia. Like I figure here we would need to think a bit about the the sizes of the strides and stuff like that. Like that's not something I want to think about right now. Like I just wanted sort of like maybe I think this at least works if you just have multiple linear layers. At least that's sort of like the simplest prototype. But one thing that's interesting about this is that like well when we're thinking about this, we can potentially just like straight up remove some ops from the forward function, right? So we potentially just here want to come in and we want to say, well, instead of 7 CNN layers, I want 3. Right? That seems like a reasonable thing to do, right? So let's say a prototype reduce the number of layers, right? Or scale them down. So one thing that's interesting about this is that here this uses the CNN layer 7. And then like no one like here these are used one after the other, so you do need to actually come in and change the names of them as well. So we can think a bit about that because you can't just delete the op. You also need to change the input and the output of it. And I figured the other thing we need to do here is that like, well, I think batch norm we probably don't need to change it. I don't know. I'm getting a sense that maybe we're making our life a bit too complicated, right? So how about we do this? So we just say, okay, so we have linear. So let's say for now, right? You know, so forget max pooling, forget all this stuff. Oh yeah, we have the self-linear layers. Yeah, that's actually the only thing I want. So let's say this is what my model looks like, right? And then that's it. That's the only thing I want to do. Great. So we have how many linear layers here? Sequential, in features, out features, 196 in features, and then 10 out features. Oh, but because this is like this, right? So then maybe we do something like, you okay? You broke something? Like, all right. So how about we do something like this actually? So we can say then, this goes from like 196 to 100, and then linear from 100 to 10. Okay, yeah. So this is a more meaningful example, right? So now what we basically need to do is we need to say, okay, well, we want to reduce the number. Well, the thing is that we need to think about this, right? Like, so add a relu. Do I have to? All right, just might as well, right? Uh, all right, so we do this, and then we say x equals relu. I forget what the in place of relu of x. Does this work? Argument type. What am I missing? Okay, so I can say relu in place true. Oh, I mean in the sequential. Oh yeah, yeah. So we can just say relu in place equals true. All right. Oh, so because linear over linear is a linear. Yeah, it makes sense. Oh yeah, yeah. You're right. You're right. It would just collapse. So I guess maybe we do this actually. I guess we do need to find a good solution where this stuff sort of changes what you need to write. But let's start thinking about it a bit. So what I want to do basically here is I can't change the number of in features and out features, right? So uh, basically in features of the first uh, layer can't change. Out features of the last layer can't change. And then everything else needs to be scaled, right? So this is sort of I think the hello world example of how this could potentially work. Um, so let's do that. And then what we'll do is we'll actually set up a training harness with this example. And then maybe we can think a bit, we can just, I guess, use the rest of the time to think about how this could work with convolutions and I guess more complex models. But let's just take this simple example and see if we can even get this to work. Yeah, so basically what we want to do is this here. So import torch, I'm just gonna say import, right? So, or is it? Right. So one thing I want to mention briefly is that ultimately we're gonna have a bunch of these transforms, right? And then when you're preparing something for inference, you would have multiple of these transform functions. Um, like basically it would look like, ultimately you're saying something like you have the quantization basic, yeah, so it would, you would have some sort of like model. So prepped model would be in a, would be model.pt, for example, right? So you load the model and then you would say something like prep for inference, right? And then this would take a model. And what this would do is it would say, like, this would have a list of transforms. So transforms, this would be a list. And then model, this would be an NN dot module, right? And then you would say for transform in transforms, model equals transform model, and then return model. So this is sort of the story I'm thinking about how something like this could actually be used. Um, and over time, I guess you just add more of these tricks, right? Like whenever you have a trick, you would do this. So let me just see the list type annotation. Sure, I'm putting it correctly. So I mean, it's a list of functions, right? So can I do that? Like basically Python annotation function. Can I just say like a list of lambdas or something like that? As that's not super important right now, but lambda, Greek. Oh, callable. Okay, list of callables, something like this. Oh no, so it'd be like callable this. Oh, I see. Okay, yeah, that makes sense. And then this would be nnn dot module as well, something like this. All right, cool. Okay, cool. So we have this. And so now let's start doing this tracing. Um Great. So well, the first step is to actually trace the model itself. So it takes the torch FX tracer and then it's gonna create a new graph. Okay, fine. And then so acquire a graph. And then we still haven't answered, I guess, how we do the transform. But let's say so this is gonna be, I mean, we're calling it a symbolic trace, right? And then it's not a CNN model, it's just say linear model. List of callable. Yeah, that's what I figured as well. Oh, list of callable, sorry. Okay. Um so let's go back here. So I do remember the inputs weren't actually like parameters of a node weren't added in the trace here. It was sort of an external data structure that you would need to access. And I think they had an example in the effects docs. Do they have an example doing something interesting here? So node.op. Okay, so let's say for node in graph, yeah. No, yeah, it's not to be rigorous or anything. It's more like to think about it's just to explain what we're doing, right? Like that eventually this is what this thing will look like. And the notebook is just to make sure we have sort of all the plumbing together like that. You know, we have a prototype for all of this and then we can then build it as a, pip library for reals at that point. Um, right, so we have this graph and then so for node and graph node, I'm gonna say print node. So this is the only thing I'm gonna do. For now, does this work? It does not work. And then this is gonna be a torch.nn.module, yes. And then, so now let's say if I call transform on a linear model, what happens? Transform is not defined. Oh yeah, okay. Transform. Okay, so let's look at what this did, right? So it basically printed linear layer 1, linear layer 0, linear layer 2. How many linear layers does this have? Why are there 3 linear layers? Oh, I think it's like the... Maybe let me not call it linear layer then, because I think that's confusing. Uh, Linear model. No, that should be fine actually. It is a linear layer. Linear layer 0, 1, 2. And then there's a graph module called with linear layers, and then this looks correct, right? So we just care about actually here the graph module itself. And so let me go back to GitHub, TorchFX. I think they had a couple examples, if I remember correctly. I think it was a subgraph rewriter, maybe. Oh, yeah, I remember where it was. So it was PyTorch discussion FX. So they had an FX forum. Yeah, okay. And then, let's see, where did James reply? 2 posts on topic. I think that was literally the only question I've asked here. So let me see if my name pops up. FX change up. Yeah, extract layer parameters. Yeah, that's what I was trying to do. So actually, this was sort of a related problem I was working on, which was like, let's say you have a bunch of convolutions that are too big to fit on the device memory. What you could do is you could split the convolution into two, and then merge it into one op. So yeah, so okay, I remember this. So Chili answered here, the module isn't stored on the node itself, but the node contains the qualified name of the module, so you can just use the qualified name to query the module name. You can just query the parameters. C PyTorch optimization.py. Okay, for pattern and patterns, what's patterns? Patterns. Oh, I see. So this lets us filter. This is great, actually. So this lets us filter out the actual operations that we need, and then this gives us the actual module. So this is actually great. This is sort of what we need. So I'm going to take this and I'm going to start adapting it. Um, okay, let me just put it here. So first off, yeah, so we have patterns. Basically, like, we're not going to call this transform. Maybe we call this half parameters, right? Something like this. And then you trace something, and then the patterns are going to be I mean, in our case, it's just linear and then dot linear, right? But potentially we would add con 1D, 2D, 3D, exactly. So maybe, yeah, maybe let's try to be a bit more realistic about it. So we can say nn dot linear, and then dot oh wait, but here it's like because it's a pairwise pattern. I see. It's okay. Let's just do this then. So pattern equals nn dot linear. Okay. So expand this potentially. Um, and then what you can do is expand, sorry, number of patterns. Oh, hey, thank you so much still for joining. Appreciate your question. Expand number of patterns here. I think. Yeah. Twitter. The Yeah, it is Christian. Yeah, he really knows what he's doing too. Like, it's nice having him. So let's see. So for node and new graph node, if matches module pattern. Okay, so and if length of node output of conv is used by other nodes. Oh, interesting. Conv is equal modules. So first off, we have these things called the named modules, right? So let's just take a quick look at what this is. So you trace something, and then dict effects model, maybe graph. Does this work? Print modules. Maybe I can skip this for now. How does this work again? So where was it? So first off, maybe let's just have a reference here. All right, so let me just double check one thing. So this when they say FX model, that's the symbolically traced model, right? So in our case, yeah, this should just be graph, right, of named modules. And then modules of node.target. So what's, yeah. So maybe, yeah, so we do this. And then so you say for graph, yo, Sudomaze, yo, Cast9, how's it going? Yeah, let me just, guys, give you a quick heads up as to what we're doing. So today what we're doing is we're trying to build a library for automatic model distillation. So basically, let's say you have a model, but it's too slow, like as in it doesn't, like the latency is too high or the throughput's too low. So there's a couple of, what you want to do is build a new model with less parameters or less layers such that the loss isn't that different. And in general, like the reason I'm interested in this problem is there's a lot of similar things like that when you're prepping a model for inference that include model distillation, quantization, pruning, like rounding up like weight values to round numbers. And the idea would be to get, you can do these kinds of transformations with libraries like TorchFX, which let you take a graph and then do manipulations on it in Python. So quantization and pruning, they already have examples for it. Rounding up weight values in distillation, they do not, right? So I think distillation I thought would be interesting. And so, yeah, so like I said, like ultimately you could, if you're preparing a model for inference, you would say like, these are all the optimizations that you would run. And then you just basically apply them sequentially one after the other, and then you just return a new model. So specifically for distillation, we're going to essentially build this tune-up model where we're distilling from some sort of original teacher model. Maybe we'll give it some sort of like parameter scaling factor or a layer scaling factor initially. So let's say, where is it? There's this is basically equals to 1 by default, equals to 1. This is nn dot module. So it's not actually a module, it's actually a trained model. I need to look into this. So basically change this. Okay, and then an optimizer, basically a torch. I guess I don't know if that's the thing, but let's just assume this is for now. So torch.n module. This is an int, and then this basically returns again a torch.nn.module, right? So yes, this is what it looks like, and I thought as an illustrative example we could download a model. So I initially said Hugging Face model, but I had issues tracing it, so I'm just going to do a regular linear model, and I'll show it to you. We trace this model, we get a symbolic graph. Then we copy the model, and we change the right weights to divide them. So basically, we look at all the weights that we can change, and we divide them. And then we can run the distillation with KL divergence and see if the whole prototype works. So transform linear model. Yeah, so what we're going to do is that we're going to say for node and graph nodes, right? So we're iterating over all the nodes in the computational graph, and this is basically, this is what those nodes look like, right? Yeah, Dbooz, nice to see you. So yeah, so for node and new graph nodes, we're going to say modules of node.target. Oh, I see. So there's this and then there's this. Let's look at this a bit. Replace node module. Oh, you can also erase nodes, I see. So they have all the cool stuff, it looks like here. Let's see. How much speed do we expect? It can be substantial. Like, I mean, basically, you can expect it to be linear in like the amount of speed up that you're doing. So if you're dividing the models by 2, then you should expect, I guess, to be twice as fast. to a certain extent, because small models don't actually benefit all that much from GPUs, like the tiny ones. Does this work? Okay, what am I actually looking at though? So if I say print conf, I haven't changed the name of the functions, I see. And then not defined, where? Graph. Pattern equals, I guess we don't really need this for now, maybe skip this. Graph object has no attribute named module. Let's see. Why do you not have so they're saying fx symbolic trace, yeah, which is what we're doing. Symbolic trace, or is it? I guess we're not doing it the way they're doing it here, so maybe let's do it their way. So say graph. You cannot. Oh no, so this is again model. So, but my model is actually called. Oh no, it is called linear model. Where is linear model? Linear model is here. Okay, I don't want you to symbolically trace it anymore. So we just have linear model. Right, linear model. Oh, so this actually needs to take in actual input, right? Net object has no attribute nodes. Why? For node and graph dot nodes, right? So we have graph is towards symbolic trace of x. For node and new graph. Okay, so they do a copy of the model, it looks like, I guess, so that they don't overwrite stuff. Oh my, I really needed like either James or Horace to yell at me for what I'm doing wrong here. Let's see. So we have a symbolic trace and then fx model, symbolic trace of model, right? And then where did they create the graph actually? New graph, fx model dot graph. Oh, I see, okay. So this is, yeah, I'm gonna call this fx model. And then this is fx model. And then this will be fx model dot graph nodes. Tuple index out of range, okay. That is fine. So what's available on the node? What does a node look like? Print node. Okay, name graph is not defined. Model, where is the graph? Okay, yeah, so ultimately this is gonna return I guess, yeah, so that's why they're doing a deep copy. So they're gonna say new graph equals a deep copy of the fx model graph, and then I eventually want to return new graph. Copy is not defined. Where is copy defined? Copy, deep copy. Copy, copy. Oh, just import copy. Lol. Okay. Okay, so we're making progress now. So let's see. So now that we can trace this thing, you know, we need to go back to the out features here, like this out feature and then this in feature. And we need to go in and change them and make them half the size, right? So How does that work then? So do we say node.target? Let's try that. What does node.target do? Print node.target. Why do I feel like this is never getting updated? It's a trap. Okay. Is this right, guys? So linear layer is 0, linear layer is 1. Print. I feel like it's using an old function to say print hello. Okay, so I see. So it's also printing the graph module that it returned, I guess, right? And then it's printing the nodes here at the top. So if I say print node, it's going to print linear layer 0, linear layer is 1, linear layer is 2. If I say print node target, so wait, did anything change besides the underscore? Oh, node.args 0.target. Okay, so let's say nodes.args 0.target. Tuple index out of range. Node. Oh, because it needs to be in modules. I see. Print modules. Tuple index out of range. Wait, is this right? Let me just copy this line as is. Yeah, so I see. We're going to say this is a new graph. Input and output are counted as nodes, I think. I see. Conv. Let me just do this. Try this new graph nodes 1 to 1. Why would I try that? I'm lost. The for loop. So you want to say to skip input and output nodes. Oh, I see. New graph dot nodes 1 2 minus 1. Not subscriptable. Oh, for node and new nodes. I see. No, yeah, I don't think this is it. It's not a list. You're right. Like, no. So I think it's back to it's like the inputs. Man, I had the example actually in some internal code. Figuring it out again from scratch now. Like, let's see. Wait, do I still have that example? Maybe here somewhere. Google Collab effects. Node list. Okay. All right, but like by the way, like once this works, I think then we can start experimenting with the distillation part, and then we would need to figure out like a more generic way of doing these op transforms. See, like there's stuff here: remove all the dropout layers from the model, extract the subgraph. Or graph and new graph modules. Let's see. So print modules. Yeah, what's going on here now? Because module is a fixed data structure, I think. That's why this is. If I say modules, well, let's not get too fancy with the traversal. Let's stick to basics. So if I say node dot target, key error x. So I can't even index into modules. But args0. What is args for module though? Let's take a look. The tuple of the arguments, so depends on the node's opcode. All accounting of uses and users updated automatically on assignment. So then there's a setter as well. Do not call it. Update arg, update karg, stack trace. So what is this? This is what an fx node is, right? So it isn't an actual module. Well, not yet. I think with Pivot, the first element is an input node. Let's see. Let's go back here. So conv modules. I feel like we're missing something super simple. So modules is a dict of fx named modules. Is that what it is? Modules dict fx of named modules, yes. Then we have a new graph. Okay, great. And then they look at a bunch of patterns. And then for each node in the graph, they check, does this pattern apply? Interesting. So argv also, like, I guess let's see, what are the properties of node? Oh, but it's on args. I guess it's a bit ambiguous. Line 66 checks. Oh, if it's a module, I see. Matches module pattern. Oh, I see. Maybe this is what we're missing then. Let's try this. For now, it's just going to be NN linear, right? So pattern, node modules. Matches module pattern is not defined. Okay. So where is this defined? Line 26 of this file. Works for length 2 patterns with 2 modules. I see. I think this is something a bit different. Okay, this actually passed this time. Oh no, it didn't. So let's try this. Now it's gonna crash. Pattern is not defined. Okay. And that's because, okay, I commented out. And then let me bring this back. And N is not defined. Symbolic trace, pattern. Yeah, okay, so torch. Zip argument must support iteration. What is this about? Clip on one frames. Like, I think this is about, like, I think the way they're using patterns here is to basically tie, like, to say that, okay, well, there's a conf followed by a batch norm. I think that's what they're doing here. Oh yeah, so look, they have something similar actually going on here. So it's basically like optimized for inference. It does conv BN fusion, dropout removal, and MKL layout optimizations. So there's sort of a very similar idea that I was talking about. Can I share the collab? Yeah, sure. Sure. The worst part is I actually had a similar example working in like I said, an internal version of this. So this is a problem I already figured out how to solve. I just don't want to open my work laptop right now. I can't stream from it. The line where it has the node up in that function here. I think this feels wrong. Node up, does that work? Node.args. I'm curious about this. Or maybe okay, how about I inspect basically I think rich inspect. Okay, wait, so I'm gonna do this very quickly. I just want to see what this node thing looks like. Otherwise, it's very hard to make sense of it. Okay, yeah. So yeah, rich is awesome. I'm definitely a fan. Import, like from rich, import inspect, then inspect node. Okay, yeah, this is useful actually. So it's saying node is the data structure that represents individual operations in a graph. They represent call sites to various entities such as operators, methods, and modules. Okay. So then we have linear layers. So we have X, and then, oh, it has its input nodes. Oh, and then it has its args. I see. And then they're going to be positional. Yeah, no, this is what we needed actually. So what we need to make sure is, oh yeah, this solved my problem, by the way. What we need to make sure is if input nodes, basically args needs to have something, right? The issue with this is that we were indexing into an empty args. That's also right. I think so. Maybe if node dot op for node in that, if node dot op equals, yeah, I agree with you on that one. Call module. Okay, let's try this. So what do we get now? Yeah, so okay, so this way we skipped the input node, right? So I think another way we could have said is if node dot if node dot all input nodes. Oh yeah, this is great actually, which really makes this problem a lot simpler. Okay, oh I see, and then it also has the call up on it, right? So now what we want to know, let's get back to the original problem, right? Which was we needed to know the fusion. Fusion. No, it's not here. Oh, yeah, no, it was here. Okay, yeah. So what we want to do is we want to say modules. Yeah, we're close. We're close. This is good. So now what I want to say is modules of node dot args of 0. What does that print? Key error. Why is this a key error? So let's just go. I think the rich thing helped. Let's do this. Let's do that one more time. I don't really have too much strong opinions, but like I like that you can add like functions as filters, but otherwise I don't have too many strong opinions about pandas. Does it have like a way to stream in data? Like if it doesn't fit into memory, does pandas still just work, or does it crash? I mean, so what if I say uh print node.args? What does happen then? Okay, yeah. I've watched the talk the other day, and it made you see a summary of the talk. Yeah, we can check that out next. Let's like do this so that like I don't wanna go up on this. So node.args.target. Okay, so node. And if I say no is arg0.target, what happens then? Okay, great. Now if I say modules on this, what happens? Invalid syntax. I mean, it is a dictionary, right? So it's going to be this and this. No, but then it should print the ones before it, right? So I don't think that's the issue. At least it's not the only issue. Modules node.arg0.target. So what if I say modules node.target? Does that work? Okay, yeah, we're getting closer, right? So now nodes.target actually has the data that we need. Okay. Like you could do a regex. No, but we're not gonna do that. It's too gross. Node.args.target. Replace node module with a fused conv. Where is fused conv defined? Uh, so let's take a. Okay, how about this? I need to take a break from FX stuff because I did have an actual example working. So maybe I will start the stream next time with like the actual working code. This is something I do want to pursue. Let's do a quick break and look at distillation a bit. So the idea here is that we are going to have a teacher model, which we're basically calling the big model, right? Like the original one we have. And then we have a student model. And ideally, what we want to have happen is that the student model needs to, it's the predictions of the student model don't need to be pretty close to those of the teacher model. Okay, so we have this KD step, and it takes in a teacher, a student, some temperature, and inputs, and an optimizer, right? And then you're evaluating this teacher, and then you're okay. So you evaluate the teacher, and then you train the student. Okay. With Torch no grad, copy the gist from here. Teacher.eval, student.train. I'm curious like what the full example looks like though. So with Torch no grad, logits from the teacher, you get the logits from the teacher on input. And then you get the logits from the student. Oh, you don't need labels actually. You just need the input because you're just getting the logits. Okay. So how about we do this? Like we could have two random models. One that's slightly bigger, one that's slightly small, and then sorry. And then this should work. And then what would be left is the effects part of this equation. But given that like I think I'm struggling with basic syntax, and I think just looking at it with inspect. Actually, maybe let's do this quickly. Sorry, I know I keep changing directions very rapidly. But let's do this. I just want to inspect what is modules actually. Inspect modules. Oh no, before the dict then. So I actually want to inspect named modules, not the dict. Okay, so this module object, okay, whatever the hell this GI stuff is, I have no idea. GI code, GI frame, GI running, GI yield from. Okay. So, I mean, maybe I print the keys then? Like, I feel like. Wait, so how to get G.I. Joe, Real American Hero? Yeah, exactly. How to get uh, keys from dictionary. The code example here, I'll share it in chat as well. Okay, oh, dict.keys is a function. Sure. Keys. Okay, so we're not actually inspecting this. I just need to print these. So maybe print modules dot keys. Okay. Okay, so there's empty linear layers. Okay, so modules that keys will actually have the name of the individual like functions basically. And I think it's not just functions because it could just be models as well. Okay, so that's good. So now if I say like just, so really if we're going to say let's say module of linear layers dot zero, something should happen, right? Okay, right? So now if I say dot args, what happens? What the hell is a linear object? Oh, linear object. Oh, oh, it's the actual like linear layer. I see. So it's not what we want. Like this has the actual thing. Okay, okay. This is making more sense. Uh, so now here, like, so this is like saying modules of nodes, right? But instead, what I want is module. So let's say this is the module, and then let's say, um, sorry. So we said these are the keys, right? So then, what is this whole arg0 business then about? Because if modules only takes in the actual module names, oh, because this will be the target of a node. I see. Yeah, yeah, this feels like it's tied to the patterns. I think the way this works is nodes.args of zero of target is actually one of the modules, right? But what we want is not the module, we actually want the actual value. How do we do this? Node.target picks the last thing. Yeah, so if you say, for example, dot target, linear has no attribute target. Oh, sorry, it's going to be node.args 0.target. That was a reference before assignment. It's not true. Lies. Oh, I see. Yeah, we went through that again already. Let's see. Okay, so we know then that modules takes in module names, but how do you get the values? Like, let's look back at I think Horse's comment again. The node contains the qualified name of the module, so you can use the qualified name to query the module itself to obtain the actual module, which you can just query the parameters. Okay, let's try that. So if I say modules of, so let's say I want to just inspect this, right? So if I say inspect is amazing, right? Yeah, you see? So it gave me a linear transformation. And so now if I say dot in features, boom. That's it, guys. We found it. Okay, so this makes sense. So really what we're doing is not like we don't really care too much about the nodes. Like we're just using the nodes to find the name of the modules that we're querying, right? But Yeah. Okay. This is making sense. So this gives you the name of oops. Sorry, the argument values. All right. So now what we're gonna do is we're also gonna take. So we have all this, right? And we're also gonna take in scaling factor, right? And then this is gonna be an int. And then what we want to do is divide these things by the scaling factor, and then we want to return a new model. Okay. So if node up is equal to call module, then what I want to do is I just want to print modules node. So what was the name of the node again? If we wanted to, did this work? Non-default argument follows default argument. Non-default argument follows default. Invalid syntax. Tracer, okay. Half parameters, okay. So then it takes a scaling factor. Let's say this is equal to 2. So print modules of node. So that we're getting a key error for linear layers of 0. Module, linear layers. Yeah, because it's not underscore 0, it's dot 0, right? So this would work if you said I mean, you know what? It's going to be very gross, but this is sort of the right way to do this. We're going to just do the hacky way, right? So we're going to say modules dot keys of so modules of so we're changing two values, right? So where was the model? Here. Right? So wait a minute. Yeah, so we're changing 0 and we're changing 2, right? And then we just want to change out features and 0, and so it's going to be so I'm just going to do it the hacky way. I think we can do it programmatically later. It'll be simpler just to know what these data structures look like. So if I say modules of linear layer 2, does this work? Linear layers, I see. What was it again? Linear layers. Oh, it was dot 2 dot n features. Okay, yeah, so we got the value. So we want to say modules basically equals basically divided by a scale factor. And then I want to print it. Scale factor is not defined. Okay, yeah, it is not defined, that's true. I called it scaling factor. Okay, it's still 100. It didn't actually overwrite the value. So let me do this. equals. Okay, so it did work. And then what we also want to do is um, modules of linear layers dot one dot out features equals modules linear layers dot one dot out features divided by scaling factor. Relu object has no attribute scaling factor. Okay, great. So I think this should be 0. 12. Why is it 12? That makes no sense. What happened, boys? Why is it 12? If I keep repeating this whole thing. Oh, I see. I see. So it's actually overriding it, right? So we need to recreate the model. So if I create this model. And then let me do this. So I'm going to print modules dot linear layers dot 2 dot n features and modules layers dot 0 dot out features. But the thing about so why are they both 25? Crazy people from the ditch. Okay. Print. I mean, let's take a quick look actually. So now I have some crazy people that live in the ditch where I live. Okay, so it actually did change the model, weirdly enough. But I think we need to we need to deep copy it. I think to your point, right? So this feels bad, right? So this should be, okay, this is very gross, but works. Ideally, this should be a deep copy instead. All right. So then, yeah, like this is why I like effects a lot, because it sort of lets you play around with compiler ideas, but all in Python. So you can do this kind of stuff. So let's assume then we've solved this. So then the problem becomes, basically, how about we do this, right? So we're gonna say, you know what I'm gonna do is I'm gonna say new model. Okay, wait, sorry. So we have this pattern. We have the effects model. So this is the model that we're getting. And then I want to create a deep copy of the actual model. So not this. So I'm going to say, let me call this model. And then what I'm going to do is I'm going to say, Yeah, you can change the D type, for example. Yeah, exactly. Like you see why this is interesting? Like, because you could do all sorts of stuff like that without actually having access to the like original code, right? Like it's just you load in a module and then you just do this kind of stuff. So I mean, I think it's great. Oh, I realize that we have 8 people online though. If you have any questions, folks, like feel free to let me know. If you're otherwise, if you're enjoying me watching me struggle, that's also great. See, maybe Horace can join. Okay. Um, well, it's different, right? Because in pandas, you're changing the D type of the data. You're not changing the D type of the model, right? Like it doesn't matter what D type your data is if you're using a higher precision. Because like what PyTorch will do is it'll upscale stuff automatically for you, and then just transform it. So yeah, so sorry, I was slow. So I want to say copy dot deep copy uh, model. Sorry, deep copy model, and then this is M, and then I want to return M. Right? So basically then I want to say M equals this. And then print linear model, and then also print M. So let's try this. Boom. Okay, yeah, it worked at the scaling factor. Boom. Okay, it all works. Uh, does it work? Print M. Yeah, it works. So you see, this works. So now we have 2 different models, right? So maybe I'll give this a better name. Um, I'll call this um, uh, well, let's start calling like let's say student model, right? That's sort of what we were getting at. Student model. Okay, and then this is going to be student model. All right, yeah, we did it, boys. You see. So this would sort of be the main idea, right? And so then the problem will be um, getting the logits from both of these models, right? So now, so we did what works. Do the node op navigation instead to get a fully solution. Okay. Well, first off, does this thing actually run? Um, so how do we do this actually? Well, first off, what's the okay? So like, there's a trick I really like. Like, you can notice here that the input it says in features 19600. So I think you can just say uh input equal torch.rand 19600, and then you know then we can say kd step Uh, well, we have the teacher, so that's the linear model. We have the student model. We have a temperature, let's say 1. We have input. And then we have um, the optimizer. So what optimizer do I give this thing? Okay, let's say this. This is our optimizer. Great. Optim is not defined. Torch.optim. Okay, optimizer. Forward got an unexpected keyword inputs. Inputs. Different bias dimensions after different distillation. Oh yeah, you would. So, oh, oh, I see what you're saying. Yeah, yeah, yeah. Okay, okay, yeah, yeah. So let's try a model with 3 layers then, right? That'll make our life a bit easier. So let's say this was like linear, and then it's like 100 to 100 to what? So this is 100, then this is 100, and let's just say this goes to 100, right? So it's 100, then there's 110. So basically either ReLU here, ReLU here later. Okay, so this is what I'm gonna call this the teacher model. Why did it not add my linear layer? Where's my third linear layer? Teacher model. Yes, it's my teacher model, no? You don't want? Did it collapse it because there's no ReLU? Am I printing an old font? Oh yeah, because I'm printing this stupid thing. Okay, never mind. Okay, great. So now we have these 4 linear layers. And instead, what we need to do is I'm doing this deep copy. Effects, named modules. Okay, yeah, so we're doing teacher model, student model sounds like a true machine learning. Yeah, I mean, that is kind of what it is, right? I guess it's a good point. All right, so I think because of like this whole input business, like we don't want to have to change the input sizes. So we're going to have to do this instead. And I think, so 0 we don't touch. Right, so this is 0, this is 1, this is 2, this is 4. So we want to change 2 and 4, I believe. So actually, wait. Oh, I see. So we can only change the ones in the middle, actually. We can't have anything that changes anything else. So let me remove the ReLUs for a second. And now let's say I add linear 100, 100. And then linear 100, 100. Something like this, right? So I can't change this one because then I have to change this one. So I can only change the hidden layers. right? And I can't even change the output or the input of this last hidden layer. So in this case, I can change this, this, and this. Okay, this is a bit more involved than I thought, but yeah, like so I guess, we have to be careful. Have to be careful that only the hidden layer sizes can be changed. All right, so let's see. So now we have, this is 0, 1, 2, 3, 4. But let's, to quickly check, I want to just print module.keys. Print modules.keys. So we have linear layer 0, 1, 2, because it's still using linear model. This is why notebooks are not great for production. Teacher model. Okay, so we have linear 0, 1, 2, 3, 4. Okay, does that make sense? We have 0, 1, 2, 3, 4. Okay, great. So we want to change the output of 1. Jamie isn't here, you are good. Exactly, I'm safe. Maybe he is, he's silently judging my coding ability. Okay, so I'm just writing these down. So linear layer 1 output. Then linear layer 2 input output. And linear layer 3 input. Okay, so let me write these down. So we have linear layer 1 output. Let me say this. Linear layer 1 dot out features. Linear layer 2 in features, but also out features. Is the ground shaking? My desk is shaking. Is there an earthquake going on? What the fuck's going on? Earthquake, San Diego. There's a magnitude 4 earthquake happening right now. Yeah, I can feel it. Come, put your hands on my desk. It's shaking. What the fuck? Oh, we live. Allah save us. Become religious all of a sudden. It's very close to us. It's like here in Calipatria. It's funny how much of a desert California is. Like, check this out, guys. It's all gray. Okay, I can't feel it as much now, but it was definitely shaking a lot. Like, Pseudo Maze, are you gonna clip that? We need more memes on this channel. Oh my god. Okay, so then we have linear back to work. Clip and ship. Back to work. No time to deal with natural disasters right now. Okay, so let's say this is our model. We don't even have a ReLU though. But we have teacher model. Is it teacher model? Yeah, teacher model is net. Okay, yeah. Here, linear model. Print, no, so teacher model. Okay, so this is the original model. Does this new model make sense? It does make sense. So this model is correct, right? So that there's no issues here. Um, okay, great. So just we have to be careful actually. So if it's a single layer model, this doesn't work, which is interesting. So that's potentially a check we could add. So okay, we're doing batch mean here, and then this needs to be 19600 always. Okay, we're getting the exact same issue though. So unexpected keyword inputs. Okay, where is this problem? So in NN modules and KD step. Okay, which line of KD step though? The first line. Great. Okay, makes total sense. It could be something in my original forward pass. Oh, I see what you're saying. Yeah. Could it be because it uses X instead of inputs? Does, does that make sense? Let's try it. I didn't know these were names, by the way. I thought it was just positional. Test KD step beforehand, yeah. But it's not even telling me which line it's failing on. Like, it's not failing in my code. It's failing a type error. Oh, a type error. Okay. Type of input. Torch.tensor. Okay. Type of teacher model. Oh yeah. Inputs. Inputs. Uh, let's keep checking types. So type of teacher model is main.net, and type of student model is also main.net, and type of optimizer. It's a torch optimizer.sgd. Just pass inputs without inputs equals inputs. What? I don't understand what that sentence means. Oh, so then this is teacher model, by the way. Okay, yeah, okay, we're getting closer. So mat 1 and mat 2 shapes cannot be multiplied. 19600 and 19600. Okay, yeah, that makes sense. So instead, the shape needs to be, I guess, 196 instead. That should just work. Ta-da! Okay, well, this actually praise the torch gods. Yeah, alhamdulillah. It's like I think God is angry because of the earthquake. Okay, so what the fuck happened though? Like, what does this do? So That was Jeremy. I think what would make that clip interesting would be just knowing exactly what was said before that moment. He heard us, yeah, I'm sure he did. Okay, so this just needs to be cleaned up a bit, right? But this is just as a single step. But does it do a step over all of the inputs? Okay, so this is what we need to do actually. So we need to basically print the model before and after and see was it actually changed. And then wait, no, maybe just see do they make the same inference, right? That's the key. So if you say teacher model dot forward on torch dot uh, rand of 100. Okay, yeah. So we're gonna say example equals torch dot rand and then 100 196 and then print torch, basically assert that teacher model dot forward of example equals to teacher model dot forward student model dot forward example. All right, so maybe we can't do an assert, maybe we can just print the value. Print and print. Oh yeah, that was what I was worried about. How the fuck are we gonna compare these two things? 3.863. Oh, interesting. Kind of not bad. It's kind of not bad, right? Like I need to clean this up into even more into a library. But I think we're good. So basically, let's say compare two tensors Python. Oh, torch dot equal. Assert torch dot equal teacher model dot forward example student model dot forward example. I think I need some sort of all operator or something. Compare two tensors PyTorch. Torch.ec. That's what I did. Dot equal. Guys, come on, don't tell me that wasn't cool, right? So let's do this. So let me just re-summarize what we're gonna do. And I think, yeah, exactly, Hackaman. So I think I'm good for today. I'll probably go take a break, but I'm not done with this project actually because I think there's a lot more stuff that needs to be done. Let's just reiterate. So at a high level, what we're looking to do is find a bunch of operations that we can do on a computational graph. Am I going to do a stream tomorrow? Maybe we'll see. I kind of just want to enjoy my birthday, I think. Maybe I'll do a late night one if I'm half drunk or something. I think that sounds fun. But probably not during the day. Um, so yeah, so there's a couple operations that you may want to do. Like let's say, for example, pruning a model. Um, yeah, sorry, you want to prune a model, quantize a model, distill a model. You may want to round up the weight values. And so eventually you want to do something like prep for inference, where you just execute a bunch of transforms. Um, and then for specifically for distillation, what you could do is something like say, okay, I want to distill a teacher model and I have a parameter scaling factor, layer scaling factor, and then the input data and the optimizer. And then you could do this, and then you essentially download a Hugging Face model, trace the model, get a symbolic graph, copy it, change right ways, divide them, and then you run the distillation with KL divergence. So we couldn't get this. We couldn't trace the Hugging Face model. I'm sorry, right? Couldn't trace Hugging Face model, so just wrote my own simple linear layer one. Um, yes, this can be collapsed without ReLU, but just educational for now. Right? So you print the symbolic trace model, and then you do these transforms here. You return a new model, and then you have the teacher and the student model, and then you just do this very simple KL divergence step, and it lets you build uh, essentially like distill a model. So now you have this model, and so maybe we could do something like uh, the predictions will be equal, be the same. And then what we could do is maybe just also print the mod parameter count. Like, is there a way to do this? Print parameter count PyTorch. Wait a minute. Aha, something's fishy. You know, the odd features look correct, right? Yeah, they are. What's going on? It's not the same model though. Like, I mean, we can see it here. Right? Yeah, we celebrated too early, it looks like. Boy, tests are important, boys. Oh, okay. Give us this as homework. Okay, fine. Okay. Exercise left to the reader. Okay. So, but yeah, I still think, okay, distillation is incredible. You can easily reach an order of This is incredible. Still BERT. Much faster than BERT. Without sacrificing much performance. Something weird's going on here. Because I think this makes it clear what's going on, right? How is this number? Which one is the student model if they are both teachers? Yeah, true. Did I put them in the right order? Yeah, I did. Just add some text here, and I can say distillation. Okay, it has two L's. Distillation. Distillation works by taking inputs. And I guess if there's multiple inputs, basically if single input, and if multiple inputs, you can say for input and inputs, KD step input, right? Is equalizing the level of teacher and student model, equality of outcome. This is not good, right? Not, let's see. Okay, works by taking the KL divergence between the student, small model, and the teacher model. And the okay, so yeah, I think the tutor model. Guys, these memes, please. Okay, so I think we're good. Like, let me just summarize one last time. So the idea was we want to do distillation because algorithms like distill BERT can be often twice as fast as BERT with a very small reduction in the performance. So it could still, let's say, have 90% of the performance at half the parameter sizes or whatever. Don't quote me on that. You can just go to the distill BERT page for Hugging Face. And when you're prepping something for infra, like FX is sort of this nice library that lets us do these graph level transforms. So similarly, we could do something similar here where you basically download a model, you trace it, you copy the model, you change the graphs, maybe you change the number of layers even, and then you run distillation using KL divergence. And then the way this would look like, so we picked, like, let's say here instead, so toy model, toy linear model. So we do this toy linear model, and then here, text, we want to say modify model using FX. It's not these memes, guys, please. Okay, confirm that the models are different. Distillation. Okay, yeah. I think we're in good shape. Like, this was good. I'm pretty happy with the result from this experiment. So I think what we'll do next time is we'll just make it work for real. So basically, I'll just say the below prototype works. To make a real one, make sure it only works over an n.linear layer pattern, and package this up into a small pip installable library called torch infer or torch distill. Um, yeah, so I did post it in chat, but I'm not done yet. No, because I don't want, like, I actually just want to finish this. Like, my concern with this thing is if I share it too much, is that someone will just take this and make the library instead, and I just kind of want to have my own like library for once in my fucking life. So it's something I've been looking forward to. So this was all the benefit of this. Models parameters. Okay, let's try that actually. PyTorch total params equals sum of p dot numal for p and model dot parameters if p dot requires grad. Am I missing anything? Parameters. Oh, I see. Yeah. I just saw it. PyTorch total params, teacher model, PyTorch total params, student model, and then print, and then print. Int object is not callable. What? What's going on? Oh, I see. Okay, yeah. Sorry. I just noticed this. Okay, so it's still the student, and then if I say teacher, uh, teacher. Yeah, it's still the same issue. There's definitely a bug here somewhere, but I think this is probably fixable because there are different models. Like, I mean, we just saw it here, right? It's not going to magically change. This was great. Actually, Sudame, I would love to take you up on your offer of a private repo. So let's do this. Like, I'll share this. Let me clean this up a bit more. I'll share it on GitHub, make a private repo because I think this could be very interesting, and I think there's a lot to do, right? Because I think outside of this, well, you could do all of this. We could figure out why some models are not supported, like the Hugging Face models. Potentially open up a GitHub issue for them as well. And so I think that there's sort of the sky's the limit here. So I think, you know what, just so I don't look bad, I'm gonna do some benchmarking right here. It's like pretend like this doesn't problem doesn't exist. All right, just carefully brush it under the rug, and then we can say, okay, well, the models are different, but their predictions are actually equal. And so this has been great, guys. I had tons of fun. Thank you so much. If anyone else is interested in working on this later down the line, feel free to send me a message on Discord. Otherwise, guys, I'll see y'all soon, and thank you so much. I really appreciate it.